Hello. In this video, I want to talk about some of the properties of stars, specifically the three topics that you see in front of you: luminosity, Wien's law, and the Stefan Boltzmann law. Those three topics are related to each other, so we're going to study those. I will begin with luminosity. Now, luminosity, in physics we call it power. It's the same meaning. So power and luminosity is really the same meaning. When we say luminosity or power, it's basically the total energy radiated by an object per second, okay? I mean, we can say per unit time, but usually it's measured in second, okay? So the total energy radiated by an object per second. What does this mean? Let me tell you in plain English. The light bulb that you have in your home, we're not talking about LED light bulb, just the classic light bulb that are, the popular ones. For example, let's say you want to buy a light bulb. So you go to the department store. You may choose a 40-watt light bulb for the bedroom because 40 light is kind of a soft light. For the office, you may want to pick 75 watts or 100 watts or something like that for the living room as well, where you want it to be a little bit brighter. You see what I'm saying? So that's basically what power is, or what luminosity is. What that means when I buy a light bulb, so here is a light bulb. Again, we're talking about the classic light bulb. And you put it in the socket, and then now it's emitting light, right? So when we say 40 watts, a watt is basically joules per second. Joule is a unit of energy. I don't want to elaborate on it, but basically it's a unit of energy. What that means is that this light bulb, this 40-watt light bulb, is giving off 40 joules of energy every second. That's the meaning of it, okay? So if you have a light bulb that is 175, for example, it's giving off 75 joules of energy every second, and so on. So the larger the amount of energy per second, the larger the wattage, or the higher the power. So going back to the word power here, the total energy radiated by a light bulb, say an object, every second, okay? Of course, we've taken the course in astronomy. When we talk about object here, we're talking about stars. You see what I'm saying? So we can reread this statement and use the term luminosity, because this is the astronomer's favorite word, not power. So what is luminosity? Luminosity is the total energy radiated by the sun, by any star, every second. You got it? Simple, I hope. Okay. So luminosity here is an intrinsic property, just like a light bulb. What that means is, let's say I have a street light. Okay, so here is the ground, here is a street light, and here is a light bulb, and it is shining. Suppose that it's dark at night. You're standing right here by the street light. There is no other street lights. Okay, so as you stand beside the street light, it's bright. Maybe you can read a book standing here. But as you go further, let's say you move further, a few feet away, it will get dimmer and dimmer as you go further and further. Make sense? Okay, so here so what's going on here? The power or the luminosity of the light bulb is constant, say for example 40 watts. But as you stand here or close to it, the brightness changes, correct? So we have another word, and that word is the brightness. And brightness here is a function of distance. How far are you from the source? This is the source, right? And brightness is dependent on how far are you from the source. Okay, there is a relationship between them. In other words, give me the power of the source, And the distance, how far are you from the source? I can tell you how bright it is at that distance. You got that? And this formula basically given in this way. We say the apparent brightness, again, this is astronomers' jargon, apparent brightness of a star, for example, is equal to the power of the source, which we called it luminosity, big L, okay, a big L is luminosity, guys, divided by 4 pi d squared. Now, the d here is how far, let me go back to the screen. So, go back to this street light right here. So, you are right here, this is the d, the distance, and this is, of course, another distance here. So, the further you are, d squared, see that? So the brightness becomes, you know, this d squared becomes a larger number as you go further, and that means because it's a reciprocal, therefore the brightness becomes smaller. In other words, dimmer and dimmer. So in other words, as d gets bigger, brightness, and by the way, the symbol of brightness in our book, let me write it here. I'm reaching the edge of the screen. AB, okay? So AB means apparent brightness. Or for short, you can just say B, big B, okay, for brightness. So let's go back to the statement. It says, as D gets bigger, AB or B gets dimmer. You see what I'm saying? So it gets dimmer and dimmer. And by the way, almost you have, this is not related to our course, but we have almost exactly the same relation for sound. You know, for example, you have a source, say a siren. So here is, let's say, a siren here, and it's making loud sound. And here is your ear. So this is how far are you from the siren. The siren is given off the power. We don't call it luminosity. We just call it the power of sound, or the acoustical power. And it is the same formula. So that loudness of the sound, it's called decibel level, is nothing but the power over 4 pi d squared, where the p here is the same as the luminosity here. So it is actually, this formula, it actually works as well for sound, because the behavior is the same. You know, the further you go from the sound source, it becomes what do you call it? Less loud. What's the right word for that? I forgot what it is. What's opposite of loudness? You know what I mean? Okay, so that's basic. But anyway, this is not our subject, but I thought maybe I'll just mention it because it is really related to it. Okay, now back to our subject, which is the luminosity. So an example of luminosity, for example, our sun, the luminosity of our sun is equal to 3.8 times 10 to the 26 watt. If you think of the sun as a light bulb, okay, as a big giant light bulb, the light bulb in your bedroom is 40 watt. What is the light bulb of the sun? It's actually this number, okay, 3.8 times 10 to the 26 watts, okay. Later on in the video, I'm going to show you the formula for this, and we're going to calculate this number and actually show it to you, okay. Another example would be the star Sirius, which is the brightest star in the night sky to the naked eye, and it is El Sabes. It's roughly 25 times as bright as the sun, okay. What that means, not bright, sorry, luminous. It's given off the source of that. Okay. Okay, good. Let me stop here regarding luminosity. I want to move on to the next topic, and then I'll come back to luminosity. The next topic, according to the video here, we have 3 topics to talk about: luminosity, Wien's law, and then Stefan Boltzmann law. So let me talk about Wien's law now. Okay. Let me write down the law first. Basically says, Wien's law says that the temperature is equal to, there are different versions for it, by the way, so this is the version in our book. The temperature is equal to 2.9 times 10 to the 6 Kelvin meter over lambda, which is the wavelength naught, or max. Let me just put max here. That's basically what the formula is. I need to explain it to you. So what it says basically is that there is a relationship between the wavelength of the light and the temperature. Okay? What that means is there is a relationship between color and temperature. I don't know if you ever noticed this, but for example, wood fire, the color of the flame is roughly reddish, orangish, right? Where the color of the flame on your stove in the kitchen is blue. And you know blue flame is hotter, just from personal experience, is hotter than orange's flame. And that's basically what Wien's law is, okay? Another way of saying it is that the shorter the wavelength, the hotter the object, okay? For example, we could say the wavelength is inversely proportional to the temperature of the body. Okay, and one more statement before I give you some example, just to kind of explain it to you. Hotter bodies emit radiation at shorter wavelengths. Of course, the wavelength. Okay, the wavelength here is lambda. Okay, the Greek letter lambda. That's the wavelength. Let me give you a table. I've seen a table here. There it is. Let me just make it bigger. Notice here, this is the color. Look at, for example, the blue color. The temperature of it is 33,000 Kelvin. Bluish, whitish is that. Let's say yellow color between 6,000 and 5,200. Red color, which is kind of the warmest, if you will, or the coolest, if you will, is 3,700. So compare red color to blue color. The blue color is the hottest of all these three. And these are the spectral type. These are basically star types. We have an O-type star, B, or our sun is a G-type star. So where if you measure the temperature of the surface temperature of the star, our star, it falls within this region right here. Okay, so that's basically the temperature of the surface of a star. And how do we know that temperature? We didn't go there to put a thermometer and measure it. Basically by taking the light coming from it, and then we would measure the strongest, or the strongest wavelength that the sun is given off, or the star is given off, and from that we can tell what the temperature is. Okay, so Wien's law basically tells us, give me the wavelength, I will tell you what the temperature is. Okay, and it applies to everything. I mean, it applies also to, you know, for example, if you're standing in front of a wood fire, you know, bonfire, by knowing the wavelength, you have some app, you aim it at the fire, the app will tell you what is the wavelength of that light that is being emitted from the flames, and from that color, from that wavelength, you plug it into this formula, 2.9 times 10 to the 6, divided by that wavelength in nanometer. I forgot to mention that. This is a nanometer. And it will tell you the temperature automatically in Kelvin. Isn't that interesting? Okay. Let me give you an example. Let me just write. So we have the temperature of red is roughly 3,500 Kelvin, the one I just showed you in the table, and the temperature of blue is roughly 12,000 Kelvin. Okay. So here's an example for you. If we look at, I don't know if you're familiar with Orion, the constellation Orion. It's one of the more popular constellation and appears usually in the winter. People in the ancient time, they thought when you see Orion, this is winter time. The Orion, which means the hunter, it looks something like this. You have what is called the belt of Orion. You got 3 stars like that, and then one here. I'm not drawing it well. Hold on. I like to draw it first as a line, and then I'll put the stars in there. Looks approximately like that, Orion. You can look it up, probably. And then you have 1 star here, 1 star here, 1 here, and 1 here. And then you get 2 stars here. They're called collectively the belt of Orion. Those 3 stars here. This star right here is called the Betelgeuse. I'm sure you've heard of it probably. Betelgeuse. I think that's how you spell it. And this star right here down there is called Rigel. I think I've heard people pronouncing it wrongly, Rigel. But anyway, it's called Rigel, this star here. So that's the Orion constellation. You know what? Let me show it to you very quickly. There it is. Kind of cool. There it is right there. Oh, there is more to it than that. So, but anyway, as you can see, the reason they call it the hunter, because imagine, you know how Roman soldier used to wear this, like a skirt, and that's the, you know, the shirt here, and there we go. This is probably a better picture. Oops, there it is. This is the one when it comes to my mind, it looks like this. That's kind of look like a Roman soldier. This is how the ancient, you know, imagined this. So it's called Orion. So anyway, this star right down there is called Rigel or Rigel. Betelgeuse, I believe, is this one right there. Okay. So anyway, back to our example. So here is our Orion constellation, and now we are asking the question. We're talking about the constellation, the star Rigel. And when inspected, we find that its wavelength, the strongest wavelength in the star Rigel is 240 nanometer, and that's basically within the UV range, you know, ultraviolet range. Now the question is, what's the temperature of that star? Given that when we aim our telescope towards it, and then we have our devices aimed at it, we receive a strong wavelength of 240 nanometer, which is in the UV range, ultraviolet range. So what is the respective temperature? So we can basically use Wien's law for that. So it said basically temperature is equal to 2.9 times 10 to the 6 divided by lambda, and the lambda that was given to us, remember you want to put lambda in nanometers, so it's going to be 2.9 times 10 to the 6 divided by 240. You don't need to convert nanometer into meter, you just leave it the way it is, and then you simply use your calculator for that. Let me use my local calculator there for you. So we have here, of course, it is 240. So we have 2.9 exp 6 divided by 240. Answer, and we get, let me put it in scientific notation. There we go. 1.2 times 10 to the 4, right? So 1.2 times 10 to the 4. So, and that would be in Kelvin. I could write it as 12000 Kelvin. So 12,000 Kelvin, the temperature. Isn't that cool? You can actually tell the temperature of a star, or the temperature really of anybody, just by receiving the light from it. You know what I mean? Okay. Now, so that's basically what Wien's law is. You don't need to know any more than that on it. Now, given that we know, so let's review what we have done very quickly. So we said that, so far we have dealt with three formulas. We said that the luminosity, which is the power, watts, and then we said, which is energy per time, the amount of radiant energy per unit time per second, how much energy, like joules per second. And then we said that the apparent brightness is the luminosity divided by 4 pi d squared. That's basically the brightness. D here is how far are you from the source that is luminous, that is emitting this light. You see what I'm saying? So those with those, and then of course the third one is that the temperature of Wien's law, temperature is equal to 2.9 times 10 to the 6 divided by lambda. Okay, so with these three equations, the question is it possible that we can actually find out what is the size of the star? In other words, let's say I am aiming my telescope to a specific star. I can measure its luminosity, I can measure its apparent brightness here from Earth, and I am able to measure its temperature and the strongest wavelength it's given off. So I have all this information about this distant star. With this information that I have, okay, can I measure its size? When I say size, basically radius. Can I measure its radius? You see what I'm saying? And the answer is yes, we can do that. So I'm going to talk about that. Before I tell you this, let me just give you an example. Imagine that if you have two objects. Two objects of the same temperature, but different size. Okay? Which object do you think is more luminous? I mean, if I was in a class setting, I would be looking at the students and wait for somebody to answer this question. But now I'm talking about myself. So imagine that, let me just elaborate a little bit. So I have one object right here, and I have a bigger object right there. Both of them have exactly the same temperature, okay? And here's my eye looking at both of them here. Which one do you think would be more luminous or brighter? Okay, my common sense tells me the bigger one, the bigger object. Let me elaborate on this. Imagine you have charcoal. Let's say you have one piece of charcoal. I'm talking about red hot glowing charcoal. Okay, and I have here three identical charcoals, similar to this one here, three of them, and they all red hot glowing. Okay, so both of them have the same temperature, obviously, because they came from the same pot, from the same barbecue, if you will. Okay, but because there are three of them here, they will be brighter. Make sense? Brighter than one, even though they have the same temperature. So with this idea in mind, what information can I get to find the size of that object that is brighter? Okay. Now, when we say the term brighter, why is it brighter? The reason it's brighter is because it has a larger surface area. Okay. Larger surface area means larger radius. So to answer the question, how do we measure, or how do we know the radius or the size of this object? This is where the Stefan Boltzmann law comes in. The Stefan Boltzmann law. I'm just going to give it to you. Basically, it says that the luminosity of an object is equal to 4 pi r squared. R here is being the radius, times sigma times t to the power of 4. Okay, this is the Boltzmann law. And by the way, I keep forgetting to mention, if you look up the our formula sheet, let me show it to you very quickly. There it is. I'll just get bigger. The luminosity of a star, which is the Stefan Boltzmann law, is right there. 4 pi r squared sigma t to the 4th. I'll talk about that in a minute. Wien's law is right there. That's the one we just talking about. And then the brightness of the star is right there. Okay, L over 4 pi. So everything is in there. This equation we're going to talk about in a minute as well. That's going to be the last topic of this video. Okay, so it's all in the formula sheet, starting from equation there is a heading called stars right there. So equation 5, 6, 7, and 8. Those are the formulas that I'm dealing with right now. Okay, back to our topic. So what do I mean? So the R here is the radius, the size, you know. And sigma here is a constant. It's called the Stefan Boltzmann constant. And it is equal to 5.67 times 10 to the negative 8 watt meter squared Kelvin to the 4th. Okay, and it's kind of easy to remember. 5, 6, 7, 8. You see that? See that? 5, 6, 7, 8. Just put the negative sign on the 8. But that would be one way to remember it. But anyway, you can always look it up. So with this in mind, so I can basically solve for R, do just the algebra, and I'll end up with L over 4 pi sigma t to the 4th and all that under the square root or to the power of 1/2. And there we go. So what that means is that give me the luminosity of the star, the power, the energy given off per second. Give me the temperature of the star. I can use this formula to tell you what is the size of the star. Isn't that amazing? You see what I'm saying? So I have a star, like our sun. What is the luminosity of that star, if I find it? What is the temperature of that star? And with this information, I can tell you the radius or the size of the star. Okay? That's how this. That's one of the reasons why this formula is very, very useful. So let me give you an example. I have on my notes here. Let's apply this, for example, to the sun. Remember, I told you if you go back to the original in the beginning of the video, I told you that luminosity. What is it? Right there. We said that the luminosity of the sun is equal to 3.8 times 10 to the 24 right there. 26. So let's prove that this is true. You can also find it, by the way, in the formula sheet right there. Right here. Whoops. There we go. The mass of the sun, what is it? Luminosity of the sun is right there, 3.83 times 10 to the 26 watt. Okay, the surface temperature of the sun is this number. We need we have to have it. And then the radius of the sun is right there. Here's the radius of the sun. Radius of the sun. See that, guys? 6.96, roughly 7 times 10 to the 8 meters. Okay, so let me use all this information to calculate the luminosity using the Stefan Boltzmann law. Okay. Okay, so let me just write them down first. So, example. Find luminosity of the sun, right? So what's given to us? We know that the temperature, we know that the temperature of the sun, the surface temperature, is 5780 Kelvin. Okay. We know that the radius of the sun is 7 times 10 to the 8 meters. Again, we are approximating it. It is 6.8 something. So with this information, we can use the Stefan Boltzmann. So the luminosity is equal to, here is the formula right here, right there. So we have here, maybe I should use a different color. Right there, this one here. So I have 4 pi r squared sigma t to the 4th for the sun. Okay, plug it in. 4 pi r squared, r is 7 times 10 to the 8 squared, times sigma, which is 5.67 times 10 to the negative 8, times the temperature in Kelvin, which is given to us right there, is 5780 Kelvin to the power of 4. Okay, and now I want to plug all of that in the calculator. Now, here's my advice to you. Don't put them all into the calculator because there's a lot of power. So just do it step by step. So here's how I'm going to do it. So I'm going to go take this calculator right here. And so I'll start with 4 pi. So that's 4 times pi is equal to, right there, 125 times 10 to the 1. That's basically 12.5, right? So that will be, I'm just going to do it step by step. So 12.5. Now, 7 times 10 to the 8 squared, 7 exp 8 squared, the square is right there, and that will give me 4.917. 4.9 times 10 to the 17 times 5.67 times 10 to the 8. And now let me get that 5780 to the power of 4. So that will be 5780 to the power of 4. Answer, it is 1.1 times 10 to the 15. Okay, 1.1 times 10 to the 15. And there we go. Now we're ready to multiply all of that in one shot. Let's just do it in one shot using the calculator. Let me move this so just to give you some more space. Right there. Okay. So let's start with 12.5 times 4.9 exp 17 times 5.67 exp negative 8, and then times 1.115 exp 15. I hope I did it right. Answer, and we get this. Let's put it in scientific notation. 3.82 times 10 to the 26. That's a really nice number, isn't it? Pretty accurate number. So we have here 3.82 times 10 to the 26 watt. Okay, and the answer, the actual answer in the let me just put it back in there. If you look at the formula sheet again, and the answer, the luminosity of the sun is 3.8326, and this is pretty darn accurate. Okay, pretty decent. So as you can see, the formula is really cool formula that we can use to calculate just about anything. You know, the luminosity of anything that radiates, that give off So as long as I know the radius of it, and I can, and its temperature, I can calculate its luminosity. One last example before I finish off this video. It's basically the same thing. It just tells you what is the size of the star Sirius in comparison to the sun. Okay, that's kind of a cool problem, and I think it's in the homework presentation somewhere, if I remember correctly. So compare, here's the example, compare Sirius. Remember, Sirius is the brightest star in the sky. Compare Sirius, which has a temperature of 10,000 Kelvin. We're going to call it T sub S. And then we know that the luminosity of Sirius is 25 that of the sun. So 25 solar luminosities, you know what I mean? So we want to know what is the radius. Basically what he wants, find R sub S over R solar. What's the ratio of the radius of Sirius in comparison to the radius of the sun? Okay, kind of an interesting example. So what I want to do, I basically want to use the luminosity formula. Here it is, just to remind you of it. The luminosity formula says 4 pi r squared sigma t to the fourth. So I want to apply this formula for both. What I want to do, since I have a ratio here, I'm going to put the luminosity of Sirius to the luminosity of the sun, and then I just work out the algebra, and hopefully I will end up getting that, okay? It's kind of a neat little problem, and it's not very difficult, in my opinion. So we have L sub S over L solar, and that means 4 pi r sub S squared sigma T sub S to the fourth over 4 pi r solar squared sigma T solar to the fourth. Okay, of course the 4 pi's cancel out, sigma cancel out. I end up with r sub S squared over r solar squared T to the fourth S over T solar to the fourth, and then here L sub S over L solar. So my goal here is to solve for that, right? That's where the formula is, remember? This one right there. So I need to solve for that. So what I want to do, let me use a different color. So what I want to do, I want to take this and bring it to the other side and basically isolate that, you see what I'm saying? So I can do that in one shot. So I have the following. So I have, go back to black. So I have here R sub S over R solar squared equals to, when I move it to the other side, it becomes R sub S over R solar. Remember, when I move this to the other side, I'm going to flip it. The numerator becomes the denominator, and the denominator becomes the numerator. So it becomes T solar to the fourth over T S to the fourth, like that. Okay. Now remember, algebraically speaking, this can be all in, would be equal to T solar over T sub S quantity to the fourth, right? This is basic algebra. So I have here R sub S over R solar times T solar over TS quantity to the fourth. And then I have those two in squared right there. So I have R sub S over R solar, and then all of that under the square root. Okay? Anyway, if you don't get the algebra, it's okay. There is one formula that is in the formula sheet that's ready for you. You can just plug in the numbers. You don't need to go through those steps. But I thought I'll do the steps for those of you who enjoy derivation. I'm sure some of you like it. So now let's plug in. We have everything here, right? So remember, L sub S is right there. Where is it? Right there. L sub S is 25 that of solar. So we go 25 solar over L solar times the solar the solar temperature is 5780 Kelvin, and then for Sirius is 10,000. It's given to us as well. It's right there, right here. That's for Sirius. And then from the formula sheet you can find the one for the sun. Don't forget that this is to the power of 4, and then to the power of square root to the power of 1/2. So those two cancel out, and then what's left here really is just to do the algebra. So what I have here are basically number crunching really. So I have 25 times, and I can use the calculator to get this number. Let me use the calculator very quickly. So what I have 5780 divided by 10,000, 10000 equals, and that's to the power of 4, and you get this big number, 0.11. Oh, not a big, actually pretty tiny number, sorry. So I have 0.112 to the power of 1/2. And then we just multiply them. So we have this one, multiply this by 25, and you get 14.45. Take the square root of that. So I'm going to do the square root. What is the square root? Right there. And that will give me 3.8. I think I don't remember getting this number. Should be doing something wrong, because I got here in my notes it's 1.7. Did I make a mistake somewhere? Let me do it again. Sorry about that. Let me do it again one more time. So let me just trash everything here. It looks like I'm doing it correctly. All right. I'm sure you're probably screaming at me now. You know the mistakes, but I'm not seeing it. All right, let's do it again. So I have here 5780 divided by 10,000. 1, 2, 10,000. That's equal to this number. I'm going to take it to the power of 4, and I'm going to get 0.11. There it is right there, which is correct. And I'm going to multiply this. So this times 25, that gives me that. Take the square root of that. I think I'm seeing the 1.7. There we go. Yes. Okay, so I don't know what mistake I did, but now it looks correct. So there we go. So it is 1.7. What that means, guys, is that the radius of Sirius is 1.7 times that of the sun. It's not much, really, almost less than double that, even though it appears to be much, much brighter. And the temperature of it is 10,000, almost double that of the sun. Where is it? I missed it. 10,000 right there. Okay? So anyway, that's basically what I'm going to talk about. I will be creating another video on apparent magnitude coming very soon. Okay, bye-bye.